Il grosso errore dell'organizzazione EuroPython quest'anno è stato l'andata di causa. Non posso mettere a fondo male.
Noi eravamo lì, però.
Okay, let's go. Welcome back in Pizza Margherita. This is a reprise of the talk NDB, the new data store library for Google App Engine by Guido van Rossum. Thank you.
Thank you. So, which of you did not see the first version of this talk? Oh, that's a lot of people, because the reason there is a reprise is not that it was such a popular topic, but that I ran out of time and I had to completely skip the second half of the slide, which was on the Asynchronous API. But because I see so many people who didn't see the talk, I'll try to really quickly go over the stuff that led up to this. But I recommend that you go to the EuroPython website and download the slides and review those at a later time, and maybe even watch the video if it's watchable. So NDB is a new Python client library. It is pure userland code, a client library for Google App Engine, in particular for the data store, although it actually interfaces with a few other things too. So Google App Engine runs your web application in the cloud. I don't think I have to say much about that. Here are some numbers. We served 7.5 billion hits one day. We have 1 million active applications, blah, blah, blah. So NDB is a sort of, it's almost the Perl 6 of the App Engine data store client, because I actually was so unhappy with the old data store client named DB that I decided to create a new one from scratch. Because we had a lot of things we didn't like and we wanted to fix those, and we just, every time we tried to fix things in the old DB library, legitimate user code started breaking because people were sort of depending on semantics that were perhaps not very well documented, but nevertheless they were depending on them, and it was difficult. So I ended up starting over from scratch, trying to fix all the problems at the same time and add a whole bunch of new stuff. So in the process, I actually also ended up refactoring the old DB, or at least the layer immediately below it, so that now you can use both the old DB module and the NDB module. If you want to, you can even use them in the same application. You should not use them for the same models, though, but it's possible in some cases to write an application that uses NDB for some models and DB for others. If you're sort of transitioning your application over, or if you're using a library that uses NDB. So NDB is very asynchronous, although there's also a completely synchronous API, so you don't have to learn anything about running asynchronous applications. It has integrated caching, it has a new query syntax, structured properties, and it makes it easy to write your own property classes by subclassing existing ones. So there's lots of other nice stuff. Very basic. You define your model class, which is actually very similar to the way it looked in the old DB library. reading and writing and deleting entities is more or less the same, except I made get is a method on a key object, and so is delete, because you don't really need the rest of the whole object in order to delete it. So that sometimes trips people over who are converting from the old library. Query syntax, I streamlined that a bit. There's this nice, what I think nice notation for querying using heavy overloading of the Python comparison operators. You can use multiple conditions and it's an implied and. There's also a way to overload OR, although you can't use the OR keyword for that, unfortunately. So there are some limitations on what you can do with operator overloading and DSLs in general in Python. So the query syntax is somewhat not perfect, but by writing your queries as class methods, you can actually hide a lot of that complexity. So what else? This is actually something that would also fit very well in the asynchronous stuff, so I'll come back to that. Structured property, you can nest one model inside another, just like in languages like C and Pascal, you can nest one structure inside another. Or you can have an array of structures, which is very useful. Transactions are exactly the same as they were before. Caching is cool. NDB actually automatically integrates caching with the memcache API. It also automatically caches entities in memory for the duration of the current request. Actually, the lifetime of that cache is the lifetime of the context object. You can create your own context and manage them. You can also clear that cache, but sort of, if you don't do anything special, you will automatically get a fresh context and hence a fresh in-memory cache each time a new request is being handled. And if you have multi-threading on, then each thread, of course, will have its own context as well. The memcache integration is somewhat unusual, but the good news is that it is completely consistent. Now, I believe that theoretically there is an incredibly unlikely corner case where it might not be consistent, but you'd have to have sort of multiple components fail simultaneously in unexpected ways. So in practice you can say the memcache integration is consistent, so you never have to worry about how long you want your memcache entities to last. You still can tune a lot of it, because maybe you have certain entities that you don't want cached at all because you happen to know that it won't be very useful. So as I said, you can override the caching in a number of ways. You can on each call say turn the caching off, or maybe turn the caching on if it's off by default. You can also, inside your model class, say, for this model, don't use the in-memory cache or don't use the memcache, but do use the in-memory cache or vice versa. You can also write a completely generic policy function. Query results, unfortunately, are not cached. That's very complicated to get that right. So maybe another time. So that's where I ran out of time on Tuesday. I think I did it in about 5 minutes this time. So now let's talk about the asynchronous part of NDB, which is both unusual and interesting, and gets high praise from those people who actually figure out how to use it. So you may have heard of PEP 342, which added a number of methods to generators in Python, allowing you to essentially repurpose generators as coroutines. So maybe I should have had a slide about what generators are. But a generator is, by definition in Python, a function containing a yield statement or a yield expression. When generators were introduced, there were only yield statements. Yield could not return a value. PEP 342 added a couple of things so that you can, instead of asking the generator, give me the next item in the thing you're iterating over, you can also say, and here is a value that I'm giving you, and when you yield the next time, No, sorry. When you resume the yield that is currently suspended, that yield will actually return that value that I'm giving you. So now there's two-way communication between the generator and its caller, and suddenly you can use it for a completely non-iterating purpose, basically as just a suspendable stack frame. Python generators have their own sort of pluses and minuses. A generator can only suspend its own stack frame. It cannot suspend the whole stack. The good news of that is that it doesn't require any sort of C-level hacks like stackless or G-event or any other approach. It also doesn't need threads, of course. But the bad news is that it can only suspend one frame. So basically, if you use them as coroutines, if you break a generator into sort of helper routines, each of those has to be a generator, and their sort of composability is different than in other situations. You have to be very sort of aware of the fact that you're using a coroutine and that it will yield. So anyway, NDB uses this coroutine mechanism that is sort of enabled by PEP 342, but otherwise not really supported by the standard library. There's no standard library support for event loops or trampolines or any other coroutine-like things. NDB has its own event loop. It also introduces a future class, which is somewhat similar to other future classes. If you're familiar with futures in Java, it works more or less the same way. If you're familiar with the futures in the standard library, in newer versions of Python, it also more or less works the same way, although for various practical reasons, the API is slightly different. If you don't know what a future is, it is basically an object that represents a value that is being produced for you by some other code that might run on a server or in a different thread or in a different tasklet in the case of NDB, where a tasklet is sort of a mini thread that doesn't really have a whole lot of stack of its own. When you ask the future, what is your result? The future either gives you the result if that offline process has already computed the result, or if the result isn't ready yet, it blocks. Now, if you look Wikipedia, if you look for futures, you'll find that they're also sometimes called promises. And there are two major categories of futures or promises. One is called explicit, one is called implicit. I think when they were first invented, the invention sort of included implicit promises or implicit futures, where you got an object, and when you use that object in any other context except passing a pointer to it around, it would automatically wait for the result. Python's futures, just like Java's futures, are not that way. Python's futures are explicit. You have to ask for the value explicitly by calling a method, and in the case of NDB, that method is called getResult. Now, the App Engine runtime is a somewhat unusual runtime. If you've used App Engine at all, you'll know that you can't open sockets directly. So the asynchronous facilities in the App Engine runtime are very different than the asynchronous facilities you find in sort of native Python, or, for example, if you're using Tornado or Twisted, or Greenlet and G-event and those kind of things. They're all based on sort of low-level asynchronous I/O, where you have a bunch of file descriptors that are all in asynchronous mode, and you have a select or a poll operation that you ask which of these file descriptors has I/O available, ready to consume right now, and it tells you this one or these 5, and then you read some bytes from some socket, or maybe you write some bytes from some socket, and then you do something with those bytes, and you go back to that poll or select loop. In App Engine, none of that makes any sense, because there are no sockets. You cannot open a socket in App Engine. In App Engine, all I/O except for file system I/O, which is all read-only and not all that important unless you're reading your own module source code. All I/O in App Engine happens as remote procedure calls. So if you want to fetch some data from a remote server, you can't open a socket to that server and start talking HTTP on that socket and sort of send a bunch of headers and body and then sort of start parsing the HTTP that comes back. No, you make an RPC call to a service that runs somewhere else in Google's infrastructure. You tell that service everything you need to it needs to do to make that request. So you send it the URL. You send it headers that you want to add to the HTTP request. You send it a body if you have a body, if it's a post or a put or something. Then that other server in the background makes a connection and waits for a response. It knows everything about HTTP. And once it has a complete HTTP response, that response with all the headers and the status code and everything else, and the body, of course, goes back to your App Engine application as the return value of that remote procedure call. So if you're doing that synchronously, you have no control over what you're doing while you're waiting for that URL fetch, as that operation is called. On the other hand, URL fetch and a number of other operations in App Engine, basically anything that is implemented as an RPC in App Engine can be called asynchronously. And that is what NDB uses here, because the App Engine data store supports that. So the idea is with an asynchronous RPC is you do it in two halves. You do all the stuff that I described for sending your URL and headers and body to Google service, but you're not waiting for the result. So you send the parameters for your remote procedure call off to a server, and then it gives you back immediately an object that represents the result. And that object is actually very similar to a future, although for sort of various traditions it's called an RPC object or a user. The class name is actually user RPC, which you never have to instantiate that class yourself, so the class name is completely irrelevant. But it behaves very much like a future. You can check if it's done yet. You can ask for a result, and if the result is already there, it just gives you the result immediately. If the result isn't there, it blocks until the remote server has done its whole thing and comes back to you. Interestingly, if the remote server sets some kind of error, then asking for the result raises an exception on your side. So that is also very natural for remote procedure calls. Remote procedure calls take parameters, they return a value, or they raise an exception. And the exception is only raised after the server has tried to do its thing and decided that it couldn't, and given you, instead of a result, an error back. So it's the same with the data store. If you want to make a request to the data store, say you have a key and you want to get the data store to give you the entity that key corresponds to, then synchronously you make an RPC that says, data store, please give me the entity for this key. The data store does its thing. It actually is a very distributed system. There's probably 3 or 4 different machines that touch your request and that sort of pass it on to each other, and they do they have some kind of enormous tree of objects where they look up your key, and if they find it, they give you a result. If they don't find it, they don't turn that into an error. They just say there was no result, which ends up sort of returning none from the RPC. In the asynchronous case, it's exactly the same. You tell the data store, here's a key, please go get me the corresponding value. And then you get an RPC object, a future back essentially, that represents that operation that the data store is now working on independently from your application, and you can go on. For example, you could make another RPC for the data store, also asynchronously, that says, oh, here's another key, give me that one too. And now you have 2 RPCs, and you can wait for those in any order. There's also a way to wait for whichever one is done first, and they may not complete in the same order that you made them. It's possible that one key you request is already somewhere cached in the back end, and the other key has to actually come from disk, so that one will take longer. Let's see. So the only other constraint, so this constrains the design of NDB's asynchronous API a lot, because we can't sort of base it on sockets and polls. There's only this one primitive operation, which is make an asynchronous RPC and get an RPC object back, and then wait for the first one to be available of multiple RPCs, or maybe just wait for one particular RPC. Another constraint is that we want to support both Python 2.5 and Python 2.7. And in App Engine, for historical reasons, those are completely differently implemented runtimes. The Python 2.5 runtime does not support threading, so NDB has to not support threading. One final remark. All the synchronous operations, both in sort of App Engine's low-level data store operations and in NDB, all the synchronous operations are always implemented using a very simple recipe, which is make an asynchronous call and then immediately wait for it to return. So if you make a synchronous call, you're really still making an asynchronous call. And in fact, if you in NDB, if you have multiple independent activities, multiple independent tasklets going on, well, you are waiting for your synchronous result. Some other tasklet might actually run and do asynchronous stuff. That's not always a good idea, but sometimes it is. So let's take an example. Here's a very simple function. This is synchronous. This is very basic NDB synchronous code. So let's define a function get or insert, and it takes an ID as a parameter. This is going to ask the data store, is there an entity with this key? Well, it's actually just the ID part of the key. And if the data store tells you there isn't, we're going to create one and insert it in the data store. Now, you could have all sorts of variations of this. This is actually also a built-in method of NDB, so this is purely as an example. You might want to integrate this with a transaction, or you might run this as part of a larger transaction. Anyway, it's very simple. Let's see if I can get a mouse pointer. Define the function, takes an argument. Employee is the model class. Get by ID is a primitive operation that asks the data store, get me one object, the one that has this ID. If that was none, then apparently that key didn't exist yet. Then we create one. You can set values in the constructor, or you can use attribute assignments to set the values. You have to tell the object this is going to be your ID. Then you write it to the data store synchronously. This is again this get by ID is a synchronous call. This put is also a synchronous call. So you make 2 synchronous calls. And then whether or not you took this if branch, you return the entity that you end up with. Now let's translate that into asynchronous code. Let's see if this actually overlays the way I want it to. Bing. Yeah. So you add a bunch of stuff, but you can sort of squint and think. You can see the similarity between the synchronous and the asynchronous version. So let me go over that. All the green stuff is new by the character. So first of all, we decorate this function with the tasklet decorator. Then by convention, my convention is, and the convention that NDB itself uses for all its public APIs, is that an asynchronous method always has a name ending in under async. Now we had those 2 synchronous calls, the get by ID call. So we changed that in an asynchronous call. Now an asynchronous call doesn't just return a value, it returns a future. here's a bit of magic. Instead of calling the get result value method on that future, we yield it. So the yield, this is a yield expression. The sort of the trampoline code or the event loop sort of intercepts that yield. It sees, oh, he's waiting for this future that corresponds to this piece of this RPC that goes to the data store. So we suspend this generator object until the data store says that that RPC is actually ready. If there's another tasklet that is runnable at the same point, we run that other tasklet. If there are no more tasklets runnable, we'll just go, the event loop will just go see, oh, which RPCs haven't completed yet, go wait for all those. And the first one that is ready is the lucky winner, and then we resume the generator that corresponds to that RPC. Well, then here nothing changes. Here we do the same thing with put. We replace our put call with put async, and then we sort of cancel that out by also yielding it. We don't care about the return value of put. However, if that put were to sort of fail catastrophically, it will raise an exception. And so that exception would just sort of bubble out of the yield, and then because we don't have a try except around it, we're not catching it. So this tasklet itself will raise an exception when you wait for its result. Now the last line, in the future there is another PEP that adds even more coroutine functionality to generators, and we would just be able to say return end. However, we didn't really foresee this use case when PEP 342 was approved, and so in Python 2.5 and Python 2.7 you can't actually have a return statement inside a generator that returns a value. You can have a return statement that just returns, because that just says I have no more results. No, for sort of this all comes from the original idea of a generator as something that produces a number of values as an iterator. So we didn't think hard enough about the use case of the coroutines, and we didn't think there would be a use case for returning a value from a coroutine in addition to yielding. There is a number of other, I should actually give priority to something called monocle that I believe 2 years ago at PyCon, Raymond Hettinger gave a talk about, which has a very similar mechanism, except monocle is built on top of either Tornado or Twisted. So it works in this sockets and select or poll loop world, or reactors as the Twisted folks call it. Their solution, I believe, was to yield the return value, and then the thing that was sort of catching the values yielded by a generator would have to distinguish between did it yield a future, in which case it was asking to be suspended until that future had an appropriate value, or did it yield something else, and then we would say, oh, that's apparently the return value. I thought about that, and I realized that that was very error prone, because one of the most common mistakes is that at some point you put this yield in, but you forget to also call the asynchronous version of the API you're calling. That's just sort of a common mistake, that you yield something that's not a future. So in NDB, when you yield something that's not a future, I immediately raise an exception that says you're not following the protocol. You have to yield futures only. You can't yield none. You can't yield anything else. Well, there's actually one exception. You can yield a tuple of futures or a list of futures, and then we wait for all of those, and we give you a list of results back. So you can also yield waiting for multiple objects, multiple futures at the same time. So then I had to figure out a different way for returning a value, and I decided that raising the intended return value was a reasonable compromise, especially since we know it's temporary, because this syntactical constraint has been removed in Python 3, or some version of Python 3. I forget where we introduced that PEP. I think in 3.3 at least it will no longer be necessary. So you have to raise an exception. I didn't want to make all keys and entities subclasses of exception. So I introduced the exception named return, which is actually a trivial subclass of stop iteration. And it turns out that if you raise stop iteration with a value, it works as well. But that's not a very good way of sort of declaring your intent. If you have no value, if you're defining a tasklet that doesn't have a return value, it's just sort of the result is nil. All it's for is for a side effect. Then you can just return or fall off the end, and you don't have to raise this exception. Anyway, that sort of one of the key things to take away here is that we're using asynchronous I/O, we're making asynchronous RPCs, but we're not using callbacks. So it's a separate rant. I don't like callbacks because even logic as simple as this one actually is somewhat difficult to express properly in callbacks, and you have to handle the exceptions in different cases. And internally in NDB, all the code that implements the consistent memcache protocol is all written in this same style. There is a sort of a low-level internal get operation that does things like ask memcache where it is. That's an asynchronous call, so that's a yield. If memcache gave us something, return that, happy. If memcache didn't give us something, ask the datastore for something. If we didn't have anything in the datastore, return none. We don't have a value. If the datastore did have something, now we have to write it back to memcache. So that's yet another asynchronous call. Except if the first memcache call gave us a special do not disturb sign, then we do not have to make that second memcache call. So there's a lot of logic here. It's like several cascades, and you want the error handling to be correct, and you want all that logic to be sort of readable, because the real version of the logic is even more complicated. So using this style, it's very easy to sort of think about that algorithm and all the state, that sort of the information about where in the algorithm am I? Have I already read something from the data store, or have I just read something from memcache, or did I not get the result from memcache? All that state is just represented the way you'd like to represent it, namely, this is where I am in my function, and these are the values of my local variables that are automatically, of course, survive across the yield. So let's see if I can finish the rest in a reasonable time, because there's a lot more to it. So first of all, that function, that tasklet, it decorates a generator. It expects that you decorate a generator function. But it returns a function that itself is not a generator or an iterator. It returns a function that sort of sends that generator off to the event queue to be started later, and it returns a future object to the caller. So it behaves exactly the same way as the asynchronous APIs in NDB all behave. So all asynchronous operations just return futures. Now, technically, there are two variations of futures. There's the sort of low-level RPC, which is its own thing, but which behaves just like a future. And there's an NDB-style future, and which you can use to wait for another tasklet, which can wait for another tasklet, which can wait for two other tasklets, and so on. Let's see, what does it say here? I'm blanking out completely. Okay, so you don't have to combine the call to the asynchronous API that returns a future with the yield statement or expression. You can just call the asynchronous API and return that future that it gives you to assign that to a local variable. Then go do some other stuff. For example, start more asynchronous calls, collect a whole bunch of futures, or just do some computation. And then when you're ready for the results, you yield a future. So you can. That's one way that you can overlap work fairly elegantly. I already mentioned that yield doesn't just take a future; it also takes a list of futures, and then it returns the corresponding list of results. So here's a very simple case. We call one asynchronous API, another one. Then we have two futures. then we do some other stuff, and now we yield those two futures, giving us two results. Now, if one of those calls raise an exception and the other return the result, that's too bad because you won't see the result. If you wanted to sort of take care of that, if you wanted to separate the exceptions and legitimate return values from operations, say you're particularly careful about exception handling, then you can yield for f and g separately, and you still sort of have this overlap actually. It turns out that the sort of yield multiple futures primitive operation is very important to sort of get your parallelism started, because that's sort of one of the easiest ways to get multiple things to start happening in parallel. So what else? I already said that futures were explicit futures. There are actually 3 different ways to wait for a future. If you're not inside a tasklet, so you're not using in a generator, so you're not using the yield statement, you can just call getResult on the future object. You can always do that. You could even do it inside a tasklet, although I recommend against it. That just blocks until the result is ready and then gives you the value. Inside a tasklet, yield f is a much shorter and much more elegant looking and also better performing way of spelling the same thing. And then finally, even though I said I hated callbacks, you can actually add a callback to a future. In fact, you can add as many callbacks as you want to a future. And once the future receives its result, all those callbacks will also be called. And they're actually, the calls to the callbacks are sort of scheduled. I have to stop!
Yeah.
That's too bad. I'm not stopping yet. Soon enough.
You have almost 5 minutes if you want, but we won't have time for question and answer.
Okay, we can't go over. It's terrible. Well, if you have more questions than fit in 5 minutes, we'll do it afterwards while we're not recording. So, it's totally legitimate to have multiple tasklets somehow share a future and all call getResult on it, or all yield it, or some call getResult and some yield it. The first one to sort of hit that point will actually block. All the others will just get a duplicate, an extra reference to the same result. And finally, as I also already mentioned, if whatever sort of was supposed to produce a result for that future actually raise an exception, that exception is stored, and even its traceback is stored on the future object. And when you ask for the result, it sort of blows up in your face and it raises the exception that was saved for you later. If you didn't want it to blow up in your face, well, you can just put a try except around it, but there's also a separate API where you say get exception, which returns an exception object, or none if there was no exception, but it also blocks. Let's see, what else do we have? The event loop. Interestingly, the event loop actually doesn't know anything about futures. The things that know about futures are the callback objects, the callback functions that sort of manage the I/O at a lower level. However, the event loop does know about the RPCs, because those are the sort of the NDB or App Engine's equivalent of using poll or select to ask for when's my next result ready. The event loop also knows about callbacks, and all the callbacks typically are scheduled through the event loop. So when you set the result and there are 7 callbacks that have to be called, those callbacks aren't called right at that moment. They're all put in the queue and executed as soon as in the event loop, and executed as soon as the event loop goes to the top. Let's see. It's very subtle. When you make a call to an asynchronous API or a tasklet, it's actually sort of, it gives you a future and it schedules a callback that is really hairy, but that you never have to know about, that sort of does all the interaction with the dependent future or RPC. That helper function, that callback, when it sees that the I/O is done, it will just tell the future, here's the result, or maybe here's the exception, if that was what happened. And that will then trigger all the subsequent callbacks, and the results bubble up. So always just use the future to wait for the result. So I think I already mentioned most of what yield does. Go read the source code of NDB to find out what really happens. It's kind of clever. You have to have a bunch of state. You call this send method on a generator, except the first time around you can't call send, you have to call next. So there's little cleverness there. And the rest I think already explained, sort of. So there's a bunch of edge cases. If the generator raises a stop iteration, that's a special case. That means that that's the generator sort of terminated, and then we actually inspect the stop iteration to see if there's a return value. Otherwise, we just return none. If it raises an exception, that is just something we have to pass on. If it returns an RPC, we tell the event loop, here's an RPC that you have to watch, and here's a callback. And so I already mentioned, if it returns anything else, that's a hard error. That means that you wrote your NDB tasklet code incorrectly. And fortunately, you don't actually have to understand any of this. Just sort of use the simple substitutions that I showed in the first get or insert code example. Sort of stick a tasklet decorator on your generator function. Change all your synchronous calls to asynchronous calls and put yield in front of them. And then change all your return value statements into raise NDB return. After you've done that, you can sort of analyze things again and see where there's opportunity for more concurrency, and then you're going to yield list of futures or a couple of futures. It's important that you actually replace all your asynchronous API calls, all your synchronous API calls in the original synchronous version of your code with asynchronous calls. Otherwise, in some extreme cases, really bad stuff can happen. I had to help a Googler who was using this sort of big time early on, and they had a mysterious stack overflow that occurred like 1 in 1,000 requests. And we finally tracked it down to them having one synchronous call in an otherwise asynchronous tasklet. So that's why naming your tasklets with some kind of naming convention is also important. The other thing that really helps is that exception handling is completely natural. I will now stop. Auto-batching is yet another cleverness where if you make multiple get calls or multiple put calls asynchronously, there's some layer in between that actually says, oh, we'll just put those calls in a queue, and then once he's waiting for a result, we're making a single get call that sends all the keys to the data store server at once, and it gets all the results back, and then we distribute all those results over the original callers. And that only works if you use asynchronous APIs. And again, the auto-batching reduces your I/O overhead by replacing, for example, 10 similar calls by a single call. And even though there's not that much RPC overhead, it still saves a lot in practice. Okay, I don't care about all that. I'll just leave this up for as a conclusion. This is not for the weak of heart. If you're just learning App Engine and the data store, I would strongly recommend stick to the synchronous API that is also more clearly documented. Start doing the asynchronous stuff when you've sort of got your application working and now you're in the process of making it more responsive. Don't start doing this right from the start. I had to redesign a lot of the NDB API in order to have synchronous versions of all the asynchronous APIs, because I found that writing sort of the Hello World style tutorial, here's NDB and here's all the cool stuff you can do with it, I had to spend too much time explaining all the intricacies of the asynchronous APIs in the first page of the tutorial. So I decided, okay, we'll have synchronous APIs as well, and the asynchronous stuff is advanced. Questions? Or timeout?
Yeah. No time for question. I'm sorry.
Wow. That's strict.
Thank you.
Well, now I have time for questions.